Hello, my name is Antti Pulkkinen and I work at the Catholic University of America and NASA Goddard Space Flight Center's Space Weather Laboratory. And in this tutorial I will give an answer to the question, why do we need more than one eye in the sky? And this refers especially to chronograph imaging of coronal mass ejections propagating in the solar corona. Now, of course, quick answer to this is that we need two eyes to build a depth perception of the objects that we are observing. You need two eyes to get three-dimensional properties of the object that you're observing. But we will look a little bit more in detail how this plays out in terms of chronograph imaging of CMEs. To set the stage for this tutorial, let's take a look at actual chronograph imagery. This is imagery taken by LASCO C3 chronograph on board Solar and Heliospheric Observatory located at Lagrange 1 point. And this sequence of images that I will be showing is for September 22nd, 2011. And let's start with the movie mode, which is one feature of Integrated Space Weather Analysis System ISWA that I'm using here. So what you see here is a moving object, moving structure in the chronograph imagery. This is of course a classic signature of coronal mass ejection, a CME. And you can see that in this imagery it's moving to the right. But now what the fundamental problem here is that now, because you have only this one eye in the sky, you are actually not able to tell if the CME is moving towards the observer, towards the SOHO spacecraft, or going away from the SOHO spacecraft. Okay, and this is something that we're trying to address by using more than one eye in the sky. Alright, so let's draw a schematic illustration of the situation that we're addressing here. Let's draw a sun first here in the middle of the canvas, right here. Let's give a little bit of color for it. Let's make it yellow, and let's use some labeling here too. I call this thing a sun. There you go. And then let's draw also the location of our first spacecraft. And let's draw one spacecraft here. Give some color for this thing also. And then let's label this thing as spacecraft C. You will see later on why I'm using this type of a naming convention for this, but for our purposes here, the spacecraft C will now illustrate the SOHO spacecraft. So what we are looking at here is now a schematic illustration in the ecliptic plane, meaning that SOHO spacecraft and the Earth and the other planets go around the Sun this way. Okay, so we're sort of looking at the Sun from above. All right. So now if we're going back here to the LASCO C3 imagery, what we're seeing here, we're seeing a CME going to the right in the LASCO C3 imagery. So let's set that also here on this canvas. So we have a moving object moving to the right in the spacecraft C in the SOHO imagery. And this is then velocity. But this is now the plane of sky velocity, so let's call it VPC. Okay. And what it means, for example, in the imagery such as one here, it means that just by observing the plane of sky velocity of the propagating CME from one spacecraft, you are not able to tell if this thing here is coming towards you or going away from you. And a little bit more mathematical expression of the same problem is here, is that now if we have the true three-dimensional propagation direction of the CME V here, it will have the projection VPC here, but we could have also the true three-dimensional propagation V going this way, and it would have identical plane of sky projected velocity vector. So just by using observations from one single spacecraft, we are not able to tell which one of these is the correct answer. Okay, so that's the sort of the fundamental problem that we need to address by means of using more than one eye in the sky. And we'll do that by adding here a couple more spacecraft to our schematic illustration. Let's put one here, and let's put some color for that, and then let's draw another one about here. Some color for that also, and let's call this one here spacecraft A, and this guy here we will call spacecraft B. All right. So, of course, now you will see that what's the purpose of this naming convention. The spacecraft A here, of course, now illustrates the location of the stereo ahead spacecraft, and spacecraft B will illustrate the location of stereo behind spacecraft. So, let's now use information from spacecraft B to address the problem that we have here. So, stereo behind provides us additional information by means of another plane of sky velocity of the observed movement of the coronal mass ejection in the stereo behind imagery. So it will provide us VPB, the projected velocity as seen, the plane of sky velocity as seen by a stereo behind spacecraft. All right. So what it means in practical terms is that if we bring here the observations from stereo behind, again I'm using the ISWA here, so let's bring in these both displays at the same time and start the movie mode also for this display. So from LASCO C3 imagery alone, you're not able to tell whether or not it comes towards the observer, towards the SOHO spacecraft. But now that you have stereo behind information also available, where you see that the CME is going to the left, you can quickly determine by using, for example, this type of a schematic illustration, since the CME is going right from SOHO imagery and it's going to the left from stereo behind imagery. The actual CME has to propagate away from the SOHO spacecraft. So by using information from these two spacecraft, you're actually able to extract three-dimensional information about the propagation direction of the CME in the imagery. And that's really sort of a fundamental reason why we need more than one eye in the sky. We need more than one eye in the sky to extract three-dimensional information about these propagating structures in the solar corona. And that ends this tutorial.